and gentlemen, the topic that I have chosen for this elite podium, that is Innovation Conference in Electrical and Emerging Engineering 2021, is model-free based single dimension fuzzy SMC. SMC stands for sliding mode control. And this is something that is related to drones actually, because my research area is drones. So can you please go on next slide? Yeah, so hello everyone. This is a brief introduction about me. The thing that have been not mentioned in the introduction, that is that I'm also the international collaborator at Condition Monitoring Systems Lab at National Center for Robotics and Artificial Intelligence, Mehran University, main campus, Jamshoro. And yeah, so this is something that is an esteemed honor, extreme honor for me to be the part of this research lab. And recently we have been collaborated with Malaysian and Pakistani researchers and got our first publication on drones. Please, next slide. Yeah, so this is the common contents of my today's presentation. I hope that the aim of this presentation is to just show you that what are the areas in drones, so that our national and national universities may focus on this area. Many of the universities of Pakistan, they are focusing on it and they are like doing wonders in that. Mehran is also one of them. They have just started collaborating with the University Technology Petronas Malaysia, which is where I am actually pursuing my PhD degree. And apart from that, NUST is also one of the elite institutions which is working in the same area. Why actually I opt for this topic is in the upcoming years robotics will have definitely a boom in the market, and it would be kind of a field where many people can go for technopreneurship. Many of the students have just what we say witnessed the presentation by Miss Aram, who was the speaker of today's event. She actually focused on entrepreneurship, but I think that if you are good at skills and you have some technical skills related to your engineering discipline or science, technology, or even mathematics, then you can turn those skills into a technopreneurship. And I think that robotics is one of the fields where you can do wonders if you have a skill set. So I've been working in robotics since 2016, I guess. Yeah, when I got my opportunity to go in University of Essex South in UK, and I've been there for 6 to 7 months to do one of the project on hovercraft, and then I developed my interest. Sorry, I developed my interest to work in the similar field. So when I got my opportunity to pursue my PhD degree over here in Malaysia, I opted for the same topic, that is in robotics, that is quadrotor. Moving ahead, please, next slide. So it's just quite, I'll just summarize this entire slide into a few things. See, the topic is underactuated quadrotor. It means that a kind of a system where you have a number of control inputs are actually less than the degree of freedom. If you see a drone which has 4 propellers, 4 fins, or 4 BLDC motors, it means that you will have 4 inputs through which you can maneuver a drone in the sky, and it can go up and down, it can do a roll, pitch, yaw. So these are the degree of freedom. So total degree of freedom are 6. And when you have less control inputs, like you have 4 motors to control and there are 6 degree of freedom, we call such systems under actuated systems. And these systems are really difficult to stabilize. The question is why people run for underactuated systems. Why? Because the most common perk or advantage of the system is that they consume less power. And if you witness the two thrust satellite in the universe, that is also an underactuated system. So underactuated system has a special kind of advantage in the control engineering or robotics engineering. Why? Because they consume less power consumption. So if you have a drone that has 6 propellers or 6 fins and a drone that has 4 propellers, obviously the drone with 4 motors will consume less power. So my topic was that slightly, the drones in today's market are no doubt very much efficient. The only problem with that is when they actually drive, or when we drive them or maneuver them in low height. So at low height, they produce a chattering noise. What do you mean by chattering noise? Chattering noise is a high number of oscillations on their propellers, on their fans, and this will be a risk factor when you are maneuvering a drone to transport a package, like in Thailand or in some of the areas of Malaysia. Food Panda and other, Amazon, they have started transporting the packages through drones. So in such scenario, when you are transporting something and your propellers are not in good condition, they have like a chattering noise, then it may fall somewhere in the middle of your journey, in the middle of your travel. So that is a big issue for the drones. And when I noticed and I went through the literature review, I come up with so many control algorithms, so many techniques, and that is why actually I opted this thing. So mainly when we convert any physical system, like we have drone today. So if we convert the drone into a mathematical form, like a state space or in matrix form, normally researchers ignore the unmodeled dynamic factors. So this is another term. Unmodeled dynamic factors can be the external disturbances, like wind disturbance. You have wind disturbance that you cannot control, but yeah, you can approximate it, you can observe it through an observer design. This is again a technical term, I guess, that the people who are here and they have like control background and who are in the final year of engineering, they might be getting these things. So moving ahead, if you and please move to the next slide. Yeah, so my theory was to present a control algorithm that can stabilize my drone properly while including these unmodeled dynamic factors. So I included three unmodeled dynamic factors. Number one is the wind disturbance. Number second is payload. If my drone is carrying any mass that is of a certain grams, and the third one is if my drone, any one of the any one of the motors, lost the efficiency of in terms of RPMs. And these three conditions, my drone must be stable enough to complete the journey. And I have proposed one algorithm for which I have like provided the stability, and the Lipnoff stability theorem I provided for that. And this is not limited to only the assimilation, but I have done the experimental stuff also that I'll show in my upcoming slide. Please move ahead. So this is the literature review. If you, I just summarize this thing in few things that when I studied about the drone and how to stabilize the drone in certain way, I come up with so many control algorithms, and I noticed that the best algorithm so far was robust control technique, that is slide mode control. And when I witnessed the papers of elite journals, I witnessed that there was a chattering noise on the fence, and that was a topic of concern for me, that how to reduce that thing. And when I studied further, I come up with another algorithm, that is fuzzy logic control. So I got an idea that nowadays what people are doing, people are hybridizing two to three algorithms together. And when they hybridize two to three algorithms together, of course the perks are maximized in this way. And I witnessed that, okay, now the chattering noise is somehow reduced. But what is the problem with fuzzy logic is, if you have witnessed any fuzzy or logic based system, fuzzy logic has intermediate steps, and those steps are computationally very heavy. And that is why our drone cannot do aggressive maneuvers. Like if the drone is doing vertical takeoff and landing, and suddenly it has to do a roll, or it has to do pitch or yaw, then it would be very problem for the specific drone. Why? Because it has a sluggish convergence rate for roll, pitch, and yaw. So my aim was that there should not be any chattering noise or high frequency oscillations on my motors. Number one. Number two, I really don't want to compromise on on the aggressive maneuvers of a drone. So I studied a lot, and then I come up that okay, the rule table of a fuzzy logic can be transformed into a single dimension. And then when you convert a two dimension into single dimension, obviously your computational load will be now de-burdenized, and now your drone can do the aggressive maneuvers. Can you go for the next slide, please? Yeah, so this is entire thing. So normally in research, people ask us that how you come up with this algorithm. So over here, you can see in point number one, this particular algorithm that is single dimension fuzzy, that has been actually used for several purposes. So you can see it has been used for deep submergence rescue vehicle, that is submarine. It has been used in double pendulum type overhead crane. It has been used in autonomous underwater vehicle and pantograph cattery system and underactuated quadrotor craft. I have used it, and the 45 reference number, like reference paper, is actually my article. So this algorithm is actually, promoting the responses of a drone when it is flying in the sky. And when something is in the sky, it has to cater many external disturbances. Yeah, move ahead, please. So I come up with a technique that is single dimension fuzzy. So when I implemented single dimension fuzzy, I come across that there are still some responses that I have to improve. And for that, I concluded that there is no any issue with the drone actually. The issue is only with the mathematical model that we are driving. Many people have used the mathematical model like linear model, and then they have linearized or non-linearized it. So this is the issue. So I come up with a model free approach. Yeah, I'll be just quick with my presentation. So if you can move for the next slide. This is the model that I have proposed. So over here, you can see the DSI, that is the disturbance actually that I have included in it. Moving ahead, please. Next slide. So this is the way how I converted this thing. I really want to talk on this thing, but this is something that really needs some background. But at this moment, I really want to say that I have converted this two-dimensional table that is of rules into single dimension, and this is how I really, managed to do some aggressive maneuvers with my drone. Next slide, please. Yeah, so this is the control block diagram for my drone. If you can see the green box, it has sub three box. One is like it's a sliding surface, and it will do some trigger the sliding rule, and then confining the state variables to stabilize my drone. And obviously it's a closed loop, so you can see a feedback going again to the reference terminal. Next slide, please. Yeah, so over here, this is the first thing that I performed in the simulation. Yeah, I have seen the message. Just give me 5 more minutes. Actually, I have been called very lately. I have been waiting 30 minutes, for my talk. So just give me the some more time. So over here, you can see that in the middle, the drone is deviated from its place. If you go in another slide, please. Yeah, over here again, you see when I included the fuzzy SMC, the issue was still there. And then if you see the next slide, again, but what is happening? The deviation time is actually reducing, but deviation is still there. Please, next slide. So now when I, propose the model-free approach, and then with my algorithm together, I was successful in, completing the trajectory. This is a helical trajectory where you can see the drone is, and these simulations are performed in MATLAB 2020A version. Yeah, next slide. I never limited myself. These are the actually performance parameters. No, there's nothing to mention about it, but this is the same thing that I'm quoting, but in terms of numerical values. Yeah. Next slide. This is the experimental stuff that we have managed to do in our lab. The experiment was indoor. So I'm still working on it because when you work the same thing, implement same thing in an open environment, obviously the parameters will be changed. Yeah. So this is the future recommendation that I have mentioned just after this slide. We go, please, next slide. Yeah, these are the error rates. Next. Yeah, so this is the thing that I really want to mention, that we really need to work on the mathematical model of a drone. It's not the only problem with the control algorithm. You have to work on the mathematical model as well if you are working for the real environment. Next. Yeah, the future recommendation I already discussed. Please go in the next slide, that is acknowledgement. This is my article. If you want to study, this is the article that is Q2 SEI indexed, and you can study it. It's available for free. Yeah, next. So I really want to thank my supervisor mentors. Number one is Dr. Saiful Azrin and Dr. Vijant. They both are from UTP Malaysia. And the third one is Associate Professor Dr. Zain Anwar Ali. He is from Sir Syed University of Engineering and Technology. Without them, it was not possible to publish and to proceed for my PhD. So I really want to thank them. Next. These are my credentials. You can pursue me. I'm really open for collaborating for any research work, especially in the robotics. I have some research papers in my computer vision and Internet of Things as well. This is my Facebook, my LinkedIn, and email address. So this is all about the topic. I was very quick because I really want to, just give a flavor of robotics, specifically the drones, so that you people can take an interest. And I hope, and I have witnessed this thing, that Mehran University and the institutions of our Pakistan, specifically the Sindh, has the potential to come and work in this area. So I really encourage, and you can directly WhatsApp me, no problem. And you can also email me. I'm currently working as a graduate research assistant at Institute of Autonomous Systems at the UTP Malaysia. That's all from my side. Thank you.